we did have a class yesterday, but it was an introductory class, and I understand that some people thought that because yesterday was a recitation that we wouldn't have class that day. But if you want to sign up, you can get tomorrow. My secretary will be in. She'll have the handouts from yesterday. Yesterday was just sort of an introduction, as far as that goes. We videotape the classes. We meet every day, in general, 9 to 10. We will have about 24 live lectures or so this semester. We will finish up about first week in March. After spring break, you'll have to do a presentation, about a 10-minute presentation. And then we will, you have to watch some other videos, and you'll get all that from the handouts and stuff that we talked about yesterday. But then you're done. I mean, there's not much to do in this class, and I describe on the video from yesterday about how I have a bad attitude about the way we educate people in schools in the United States right now, that we just teach them how to take quizzes. And so we don't have any quizzes. We don't have any final exams. You really don't have to do too much. I would appreciate your asking questions so that I can diverge and think of a story to tell. Just like you came in and said something about, you know, the snowstorm and how fast it's coming. So I tell the story of the blizzard of '78, right? Not that it's relevant to anything here, but are we on now, Nicholas? Okay, so to start today, I want to take some Sprite Zero, and basically all I wanted, I could have used club soda, but I wanted something that if I pour it in here, you'll see the CO2 evolve. Okay? Suds, foam. Okay, they're not really suds, they're foam. And I want you to watch how quickly that dissipates, the gas dissipates. And we're going to talk about it towards the end of class. And this all relates to, by the way, this is sugar-free. I don't want to spill it all over the table and get everything sticky for the next class. This relates to the Achilles heel of steel. See, I don't know if I ever told you the Achilles heel of steel, those of you who took the class last term. Anybody know what it is? It's called hydrogen, okay? And what you just saw, this is a CO2 coming out of a soda, is time-wise an almost perfect analogy for how fast hydrogen comes out of steel as it solidifies over the next 48 hours. This will be flat and have no zing to its taste, right? In 48 hours. You saw how fast hydrogen came out, or CO2 came out and bubbled away, and that's about how fast, once the steel starts to solidify, it's rejecting the hydrogen. And it continues. You see some bubbles coming up here, and you'll see them at the end of class, but there'll be fewer. And we'll talk about hydrogen, but in processing of steel, there are specifications that say if you introduce the hydrogen from welding or electroplating or any other process, you have to put it in a furnace and bake the hydrogen out within 1 to 44 hours, because if you don't, you could form cracks. The hydrogen can form cracks in the steel under certain conditions. We're going to get to talk about that more than you ever wanted to know about that today, at the end of today and tomorrow. But to begin with, I wanted to show you, you saw the bubbles, and now you continue to see bubbles, but the rate has decreased dramatically. And in fact, when you try to measure hydrogen content in steels, when you weld the steel and then want to measure the hydrogen, if you don't quench it in liquid nitrogen, within 1 or 2 minutes, you lose half your hydrogen, okay? Because it's coming out just like the foam, you know, the foam in the soda, okay? So a visual will give you something to remember, right? I could have told you that, but it won't be the same as having poured three cans of Sprite into a beaker. Does anybody have any questions? I know I haven't given you the introduction to the class, but you'll get the introduction. And all you really have to do is come to class each day. Except there might be some days, and maybe this Friday will be one that we might cancel a class, but in general we'll have class every day between now and when we finished up about 24 lectures. But I want to talk about welding metallurgy today. We'll get to this in a little bit. But I have to give, and I apologize to the people who took my class last semester, but I have to give a little bit of an overview. Last semester I talked about an introduction to material selection, and I handed out, and if you've already got this, you don't have to take this again. This is sort of an article that I wrote once a couple of years ago on selection of materials and cost of materials. If I had to give you a 3-page outline of the 12 hours of lectures I gave last fall, that's it. But in that, those of you who were here last semester know that I kept on talking about steels and sort of apologizing. Why does he talk so much about steels? And anyone want to give me the answer? Anyone remember the answer? Steels are 95% of all metals made. Okay? And if I look at tons produced per year, steel is 1.5 billion tons. The next most common metal is 45 million tons. So, and if I get to other things, stone is the most. I've estimated at 6 billion tons in the world. Cement as structural materials is about 2.2 billion tons. These two are obviously more than steel. And plastics, all plastics combined are only 300 million tons. So the plastics industry on a weight basis is 20% of the steel industry. So yes, we will talk a fair amount about steel because it's an important material. It is, as among structural materials, it's the predominant material. Now you can say, well, what about aluminum in automobiles? Well, yeah, they've been making all aluminum Audis for years, 20 years. They made an all aluminum Duesenberg in the 1930s, or a Pierce Arrow. There's a picture I have of J.P. Morgan standing next to his all aluminum Pierce Arrow. But those were not consumer cars like a Model T. And the Ford Taurus is still made out of steel. Yeah, you can buy a $90,000 Audi. It's all made out of aluminum. And you're going to soon be able to buy a Ford F-150. That's not all aluminum, not the frame rails. They're still steel. But the body is going to be aluminum. They haven't announced the price. This summer they'll announce the price. Anybody want to bet what the increase in price is going to be? I mean, let's just say the base F-150 right now is about $30,000 truck. You can put all the other bells and whistles and get it up to $55,000, but it's a $30,000 vehicle. Anybody have an idea? Want to guess what you think the all-aluminum F-150 is going to cost? I'll bet you it's in the $40,000 base price range. It'll add a third to the price. That's my prediction. Okay? But it's going to blow away all the other pickup trucks on gas mileage. It's the most profitable vehicle for Ford. They're making $10,000 on every one. So they're going to take a big risk of coming out with a high volume vehicle. The first people ever to do it. It was 25 years ago that I said it will be 25 years before we see a high volume all aluminum vehicle. And well, maybe it was only 24 years. Okay, but it takes about that long. So in any case, that's why we're going to talk about, well, we're going to start out weldability talking about steels. And you have to first, well, one of you in last semester's class asked me, well, why are there so many steels? If you go look in handbooks and stuff, you'll see lots and lots and lots, hundreds of different steels. You first have to ask, well, what is steel? Define steel. Does anybody know how steel is defined? It's an alloy of iron and carbon. Very good. So I just happen to have somewhere here an iron carbon phase diagram for you. So you can pass that around. But I gotta figure out the exposure on this thing. Anyway, that's a little overexposed. But anyway, I'll figure that out sometime. So I don't know how many of you understand phase diagrams, but you plot temperature versus the amount of carbon in the steel. And this, actually, if you look down in the corner, you'll see the name of John Chipman. And those people who've been to our departmental conference room, it's called the John Chipman Room. John Chipman came to MIT in the late 1930s. He was a physical chemist from Georgia Tech, and he taught people how to make steel with consistent composition. And he impacted and had a tremendous impact on this industry. This phase diagram was evaluated. He retired in '62. This phase diagram he published in '72 when he was 75 years old. So John and I remember going as a young assistant professor to meet with John Chipman and ask him some questions when he was in his 80s. So he was still working on things. But the interesting thing about steel, this is the liquid region at high temperatures above 1530 degrees C. The steels are on less than 1 or 2% carbon, and they have this region called austenite here. The cast irons are also on this diagram. They're things that are above about 2.5% carbon. So the cast irons are in here, the steels are over here. The interesting thing about steels, and one of the things that gives them a lot of their weldability, is they transform from body center cubic to face center cubic at a temperature somewhere between 723 and 910 degrees centigrade, depending on the carbon content. And because of that transformation, which is a solid state transformation, the steels can give you very fine grain size. And very fine grain size in most metals gives you very good strength. So it turns out I can weld two pieces of steel together and just let them solidify without doing anything special, and I'll get 100% joint efficiency. That's not true in many of your other materials. It is true in steel, and it's true in titanium. Titanium has a phase transformation like this. And a system that gives you a crystal structure phase transformation that leads to a refinement of grain size naturally will give you very good joint efficiency. You go to aluminum, and you're going to see we have some problems getting 100% joint efficiency. Okay, what's 100% joint efficiency? You weld the bar together, and you pull on it, and you get the same strength as the base metal. We're going to talk about, well, do you want the same strength? Or what happens if you use undermatching filler metal? So it would always fail in the weld metal. Or do you want overmatching? And how much overmatching? Well, it turns out the answer is you do want overmatching for good mechanical behavior reasons, but we'll get to that and talk about that as we go along. But this is the iron carbon phase diagram. All steels are based on this, and in fact, the steel industry, starting probably 100 years ago or more, divided steels into carbon steels and low alloy steels. Or actually, they call them alloy steels, but we really call them low alloy now. And they also, well, they have high alloy. Carbon steels contain only carbon, manganese, sulfur, phosphorus, and usually silicon. Okay, if they have any of these other things like nickel or copper or chromium or molybdenum or high manganese, and high manganese I think is above 1.25% or so, they're called low alloy steels. And the alloy content might be, let's say, up to 2 to 3%. High alloy steels is greater than 4% typically. And if you get high enough alloy, you can get steels that we don't even call steels anymore. When they're less than 50% iron, we start calling them nickel-based alloys or cobalt-based alloys. There's an entire system, and when Mike Balforth talks about stainless steels, he'll show you a genealogy of steels similar to what I showed the class last semester. But in any case, carbon steels historically were dirt cheap. They were priced differently than low alloy steels because it was much more difficult and much more expensive to make low alloy steels because you had a lot of alloy content. And how much cost was there? Well, if I add nickel to steel at a 1% level, I'm adding $130 a ton. What's the typical price right now if I went out to buy some carbon steel plate or bar or something? Anybody know what it costs per ton for a ton of steel? Approximately. That's if you're buying in low quantities, but if I'm General Motors, I'm going to be paying $400 a ton, which is only about 80 cents a pound. Right? No, 20 cents a pound. Sorry, it's 20 cents a pound. So some of it, well, so carbon steels right now, the cheapest bar stock is probably $400 a ton. Reasonably good quality automotive sheet might be $1,000 a ton, so it's 50 cents a pound. This is in, you know, I'm going to go out and buy 100,000 tons. I'm General Electric Appliance Park, where they make washing machines and refrigerators, or I'm General Motors. They're going to negotiate prices of $1,000, $400 to $1,000 a ton. If you're talking low alloy steels, the prices can be anywhere from $800 a ton all the way up to $10,000 a ton or more. Okay, and if I'm talking high alloys, I could be talking, now you're in your $4 a pound range per ton, $16,000, right? Or $8,000 is $4 a pound. But if you get to the nickel-based alloys, the high nickel alloys, you could be paying $30,000 or $40,000 a ton. So we build nuclear reactors out of these things, out of great big thick plate, but it's not cheap. Okay, nuclear reactors cost, right now, what's the cost of building a nuclear reactor? Well, you can't do it because the environmentalists will take you to court for 10 years. But if you could build a nuclear reactor, what would one cost? You're a nuclear physicist.
4 billion.
Yeah, 10 billion is a good number. 4 billion, I'm not sure. You're going to have a very friendly country, okay, to build. You could build one for 4 billion. Yeah, and it takes about 10 to 15 years to get certification, which is one of the reasons the cost keeps jumping. But, so it turns out they use high alloys. They're going to use the best alloys. But again, this gets into a matter of cost. If you're going to make an automobile, you're going to make it out of carbon steel, if you can. Or you're going to use a very low alloy steel, so far as that goes. What is it that makes... well, there's a number of things mechanically that make steel attractive, but one of the things that we want from all kinds of materials, since the dawn of creation, people have liked to have something that's easily formed. I can take clay and I can form it when it's soft, and I could make a paper clip holder, and then I can put it in a furnace and I can heat it up, and we call it pottery, and it comes out nice and brittle but hard. And so it has wear resistance, and not with whole paper clips, but now I can put water in it, and I could grind my cornmeal in it. I can do lots of things, right? So I'd like to have something that's hardenable, to be formable, soft at low temperatures, and somehow transform it. You know, pottery clay was one of the first things that they learned to harden, but it turns out other things can be hardened, and steel can be hardened. And so steel can have strengths from 30 KSI, or if you're if you like to use megapascals, more and more students want to use megapascals, 200 megapascals up to 700 megapascals, and even up to 1.4 gigapascals, okay, type of strengths. That's 200 KSI. And it can go higher than that. I mean, aircraft landing gear are 250 KSI, or what's that, 1.7 gigapascals or something, strength. So you can get tremendous hardness out of steel, and that's because the steel can transform at high temperatures to this face-centered cubic austenite phase, and if you quench it, you can get a metal stable phase, which is not this body-centered cubic ferrite, but you can get something called martensite. And martensite's as hard as a file, okay, a steel file, so far as that goes. So you like to have something that can be hardened. There are other alloy systems that can be hardened. Aluminum, we're going to talk about aluminum, but aluminum is precipitation hardened, okay? You heat it up and you cool it down, and then, or you quench it. You heat it up, solutionize everything, quench it, and then you bring it up to an intermediate temperature. We call it tempering, and you get little precipitates. And some people will tell you that's nanotechnology. Well, the Wright brothers used nanotechnology in their engine, okay, at Kitty Hawk. It was an aluminum copper alloy that had been precipitation hardened. Aluminum for lightweight, because it's an aircraft. Precipitation hardening, so it had decent wear resistance. And it's still sitting in the Smithsonian today. Cast iron is more than 2 or 2.5% carbon. More than carbon steel, because cast iron is a eutectic. If I look at the melting point here, cast iron, you'd like to have something that is low melting to make it easy to cast. Huh? Well, historically they call it cast iron because if you took iron ore where you didn't necessarily want carbon, you weren't looking for carbon, you would mix iron ore with coal, or originally, if you go up here to Saugus Iron Works, they mixed it with charcoal, okay, which is carbon, just a wood source of carbon, right? And when you do that, and you try to melt it, you will form, the carbon will alloy with the steel and form cast iron. So in the 1600s, they didn't have the phase diagram. But it was cast iron that melted at a low temperature. They then could take that cast iron and beat it and forge it and everything and heat it up. That's the blacksmith, you know, folding it over and making swords and stuff. As he did that, the carbon would burn off the surface. And if he did it enough, he burns off enough carbon, he would get something that was even more malleable, more ductile, that was wrought iron rather than cast iron, because he had wrought it on the forge. And if he did it long enough and didn't oxidize it all the way to nothing, he would end up with steel. Okay? So historically, they would take iron ore, reduce it with carbon, and end up with cast iron. Then they would sort of work their way back across the diagram, and if they're lucky, they can end up with little bits of steel, which were tremendously expensive. Okay, all that work that went into things. I've estimated the person hours per ton in the 1600s was about 2,000 person hours, maybe 3,000 person hours per ton of cast iron or wrought iron. Well, today it's about 20 minutes a ton. Okay, so look at that productivity gain. And what was the big productivity gain? It was 1856. Sir Henry Bessemer taught us how to build a vessel so we could burn the carbon out of the cast iron more efficiently without oxidizing all the iron back to the ore. Okay, that was the beginning of the Iron Age in 1856. And who was the Bill Gates of his day, the richest man in the world? Carnegie, Andrew Carnegie. In his day, he was richer than Bill Gates or Warren Buffett, okay, on a proportional scale. And it was all because of the railroads and steel, okay? So there are certain things that came along, but the reason it's called cast iron is because that's how it was made originally. You take charcoal and iron ore, reduce it, and you end up with cast iron, which is right here on the diagram. All the cast irons are somewhere around, this is about 4.3 or something. But you can have cast irons are down here, you can have cast irons up here. You don't go above 5 or 6% carbon in cast iron because you run into other problems. Yeah. It actually, to tell you how it happened, was in the United States we had some iron ores that were very low in phosphorus, and so we could make good steel. Okay, in Czechoslovakia, a lot of the Europeans, the Czechoslovakians were some of the best steel makers in Europe, And the Czechoslovakian iron ore and things had a lot of phosphorus in them, and they had a lot of sulfur, and they would try to make their steel. They could not get consistent results. It wasn't until John Chipman came along in the 1940s that really taught people how to get consistent results. But you don't just take iron and carbon and put them together. You put them together with a flux, and that flux might be limestone. It could be calcium silicate, which is the geologists call wollastonite, just a rock, okay? They might throw sand in there, okay? So they throw in these different things into the steel when they're making the cast iron, which you're going to then turn and burn the carbon off and make steel out of that. But if you have very much silicon, or very much sulfur, you've got a real problem, because if I had the iron carbon or iron sulfur diagram, the iron sulfur diagram has a really deep eutectic with the sulfur. If you remember, sulfur is right underneath carbon on the periodic table. And it turns out here's your eutectic with carbon. The eutectic with sulfur is an even deeper eutectic below the hot working temperature where you're going to forge that steel. And so you'd form liquid iron sulfides on the grain boundaries, and they call it hot shortness or hot tearing. And when you try to roll or forge the steel, it just crumple into pieces because of the liquid iron sulfide. And someone learned if you throw some manganese in, the manganese will form stable manganese sulfides that melt above the melting point of steel. So manganese is merely a way to tie up the sulfur impurity that comes from your coal. Okay? And then they had problems with phosphorus, and they had to learn to use what they call basic refractories, like calcium-containing refractories. Things that, well, there's acidic, which is, and I hate these terms, but people were chemists back then, okay? And they knew acids and bases. And the silica-based slags were considered acid, and the basic slags were based on calcium or magnesium, okay? Calcium hydroxide, magnesium hydroxide. Silica would tend to form acidic mixtures with things. They make no sense to me today, but they made sense to the people who were basically working with chemists who were working with water-based systems back then when they thought about these things. I went back to a 50-year-old book on welding metallurgy, which was written in the mid-60s. And he didn't even list the basic oxygen process, which is how all steel's made today, because it didn't come into being until like 1970s. But even back then, if you read, even today, you read specifications, it said it can be made by the acid process or the basic process. And that's just a question of, you got iron and carbon, and what is your other constituent? Your slag is going to be made out of wollastonite or sand, or it's actually made out of a bunch of these things. But what's the composition of it? So John Chipman came along and taught people, well, other people learned in the 1880s, you throw some manganese in. And I read one book, and they said the definition of steel is an alloy of carbon and manganese, because there is no steel that's made with zero manganese. In the old days, like before World War II, there would be a rule when you're welding that your manganese sulfur ratio had to be greater than about 3 and preferably greater than 6. Okay? You had to have enough manganese so you didn't get this iron sulfide intermetallic in your weld metal and have the weld break in two as it cools down from cooling shrinkage stresses and stuff. We don't worry about that anymore. No one has sulfur that high anymore. Okay? Back, if I go look at an ASTM spec that was originally written in the 1920s or 1930s, it will say the sulfur must be less than 0.05%. And so that's, let's say, 1920s. And by the 1940s, they were saying the sulfur must be less than 0.04%. Okay? By 1975, when Tom Eager was working for a steel company, the sulfur was typically less than 0.01%, and the Japanese were making it at 0.005%. Okay? They had modern equipment, and they were beating our socks off in quality of steel. So you want to have the sulfur very low in almost every case. 0.05%, 500 parts per million, was about the best they could do in the 1920s with any regularity. They didn't know how to control it until John Shipman told them what types of slags and stuff to use. By the 1940s, you'll see 0.04. I can go to ASTM spec and I can look at the spec, and they'll still have today, say the sulfur has to be less than 0.05. Are you kidding me? No one makes an 0.5 steel anymore, okay? They haven't made it since before 1950. They got to this, and then they were getting to very low sulfur. Sulfur does a lot of bad things for toughness and other things in the steel, but we've learned how to make it better and better. We can regularly get down to 002 or 001 sulfur today if we want, but we don't usually need to. Yeah.
Yes, I just, you know, I think it'd be nice to talk a little more about the slag, because you mentioned it a few times, and I know it's an ionic phase.
Right.
You know, lower densities, it's on top, it's at very high temperatures, you're close to equilibrium, but I'm not sure that everyone here, you know,
Yeah, okay. Yeah, so if you go up Saugus Iron Works, they got this big shaft furnace, and it actually is on a hill. So this is the grade of the hill, and this is about 15 feet above the bottom down here. And they would pour in charcoal, iron ore, mostly, well, that's probably Fe203. They basically got it out of the bogs here on the seacoast. They'd go out there and, anyway, and they'd add sand or limestone. Limestone is calcium carbonate, if you will. It could be magnesium carbonate. This is basically silica. It could have some manganese oxide. It could have some titanium dioxide. It could have lots of things in it, in the sand, depending on what you got. You throw these things in the top, and this shaft furnace, they used to call them, they still call them the blast furnaces, and they blow the air in here. They have great big bellows down here, okay? And they have a water wheel that's pumping this bellows and blowing air in here, and you're burning up the carbon, the charcoal, generating heat. It's really hot down here. It's cool here because you're dropping the stuff in here, and the particles, you have a particle bed reactor here. You're sending CO2 up the stack, or actually carbon monoxide up the stack, and down here you'll generate on a hearth of sand some cast iron. Now, this cast iron will also have a slag on top that forms on top, and it's basically a molten glass. It's a calcium silicate molten glass. If you pour it out on the ground, you can hit it with a hammer after it cools off and it shatters like glass. And in fact, you can find obsidian, which is a natural glass formed from volcanoes and stuff, and it's basically you just melted a bunch of sand, and this becomes the slag. And the slag is where you want your impurities to go. You want some of the sulfur will go up the stack, some of the phosphorus will go up the stack, but a lot of it gets trapped in this molten glass. So now it's a calcium silicon phosphoric acid glass, okay? Or it's got sulfates in there. It's just a complex liquid ceramic mess, okay? And people, like I said, people in this part of the country could make really good steel because they had really good raw materials. They didn't even know what made them good. People in Czechoslovakia had to deal with all this high phosphorus ore, and they were beating their head against the wall until someone figured out, oh, let's throw some manganese ore in here. We get better results, and it doesn't crack when we start to forge it and everything. Is that kind of what you wanted?
Yeah.
Okay. to help them understand some of that. So I don't want to go too far on all of that, but I do want to tell the story of, you've heard of pig iron? Okay. Does anyone know how the term pig iron came to be? Okay, so every now and then, about once a day, you would tap the bottom of the furnace. You would actually have a little clay plug that you put in around this sand hearth, and you would basically go in there with some steel rods and you'd poke away that clay plug that you put in there, and you would allow the liquid metal to flow out of the furnace. And if you go up to Sawgrass, you see the guys, they basically, the floor around the caster was basically just about 2 feet of sand. And they would dig a little trough in the sandy floor for the liquid metal to flow out through that trough. And so if it's coming out of a trough out of the furnace that looks like this, they would then flow it into what you would call a manifold, okay? And off the manifold, they would have little castings like this. So the metal would come and it would solidify on the sand floor. They've dug this stuff in the sand. It's like people at the beach playing in the sand, right? And these were the pigs. And it's called pig iron. They would make little castings. It might be a 40, 50-pound casting like this. It's a piece of pig iron. And this bar, anybody know what this bar is called? It's called the sow bar. What's a sow? Some other pig. Those are the piglets nursing off of the sow bar. The sow bar might weigh 400 or 500 pounds. If I'm going to make a cannon, I use the sow bar to forge the cannon from the sow bar, and I got to have,